July 9, 1943. Kure Naval Arsenal, Japan. Chief Petty Officer Takeshi Yamamoto, 34, from Yokosuka, pressed a micrometer against the brass valve seat. The reading showed 0.03 millimeters of corrosion pitting. His chest tightened. 6 months of failures. 17 prototype weapons tested. Every oxygen regulator corroded within 72 hours of saltwater exposure. Type 93 torpedoes were supposed to revolutionize naval warfare with 40,000-meter range. Instead, they sputtered out at 8,000 meters, barely farther than American Mark 14s. What Yamamoto didn't know, within 96 hours, his next decision would sink 3 Allied cruisers and extend torpedo range to 20,000 meters. His unauthorized modification would change Pacific naval tactics forever. The problem wasn't the torpedo's revolutionary oxygen propulsion. Engineers had perfected that in 1935. Pure oxygen combustion produced no visible wake. Enemy ships couldn't detect torpedoes until impact. But the system depended on brass regulators that controlled fuel flow at 450 pounds per square inch. These regulators, manufactured to peacetime specifications, corroded catastrophically in combat conditions. Could anyone solve a problem that had stumped Arsenal engineers for 6 months? Yamamoto walked past rows of disassembled weapons. Each Type 93 cost 25 million yen. Each contained 490 kilograms of explosive. Each represented Japan's technological advantage over American naval forces. But advantages meant nothing if weapons failed before reaching targets. Commander Hiroshi Tanaka entered the workshop. Chief, destroyer Jintsu deploys tomorrow morning for Kolombangara operations. She's loading 24 Type 93s. How many will actually work at combat range? 6, Yamamoto said. 8 if conditions are favorable. Tanaka's jaw clenched. Intelligence reports 3 American cruisers and 10 destroyers patrolling the Solomons. 6 functional torpedoes won't stop that force. The numbers seemed impossible. Japanese destroyers would face 13 enemy warships with weapons that had a 67% failure rate. But Arsenal test logs confirmed every detail. Yamamoto returned to his bench. The corroded valve seat sat under his magnifying lamp. Microscopic pits covered the brass surface, tiny craters where saltwater had eaten into the metal. These imperfections created leak paths for high-pressure oxygen. Leaks meant fuel waste. Fuel waste meant torpedoes running out of power at 8,000 meters instead of their designed 40,000-meter maximum. Standard procedure required replacement parts machined to original specifications. But original specifications were the problem. Peacetime tolerances assumed ideal storage conditions. Combat reality was different. Torpedoes sat in humid magazines for weeks. Launch tubes flooded with saltwater. Temperature swings stressed metal. The brass valve seats couldn't survive these conditions. His assistant, Petty Officer Kenji Sato, watched from across the workshop. Chief, new parts will corrode the same way. We're just repeating the failure. I know. So what's the solution? Yamamoto picked up the valve seat. Light caught the pitted surface. Brass corroded in salt water. Steel corroded faster. Copper was too soft for pressure applications. What material could withstand both high-pressure oxygen and seawater exposure? The answer hit him. Not a different material, a different surface. Bring me the electroplating equipment from the coating laboratory, and find every gram of chromium in this arsenal. Sato's eyes widened. Chromium plating? Chief, that's for decorative work. Naval regulations prohibit unauthorized modifications to weapons systems. Regulations also prohibit deploying weapons that don't function. They believed the risk was acceptable. They were catastrophically wrong about the consequences, just not in the way Sato feared. Chromium created a passive oxide layer that resisted corrosion. If Yamamoto could plate the valve seats with a layer just 0.005 millimeters thick, it might prevent saltwater pitting while maintaining dimensional accuracy. The oxide barrier would self-seal, protecting the brass underneath. Unlike organic coatings that degraded under pressure, chromium oxide remained stable at 450 psi and temperatures up to 200 degrees Celsius. The theory was sound, but theory and practice were different. Electroplating required precise control of current density, temperature, and solution chemistry. Too thin, and the chromium wouldn't provide adequate protection. Too thick, and the valve seats would bind inside regulator housings. Yamamoto needed exactly 0.005 millimeters, 5 micrometers, across every surface. He had no precision plating equipment, just laboratory glassware, a power supply, and a thermometer. Industrial facilities used computer-controlled systems. Yamamoto had his experience, and 18 hours before Jintsu began loading weapons. Sato helped set up the plating bath, glass container, chromic acid solution. 2 electrodes, one connected to the valve seat, one to a chromium anode. When current flowed, chromium ions would migrate and deposit as metallic chromium on the brass surface. Simple in theory, unforgiving in execution. "If this fails, Commander Tanaka will have us both executed," Sato said. "If we do nothing, Japanese sailors die when their torpedoes fail." Yamamoto connected the power supply. "I'd rather face Tanaka than explain to families why their sons drowned because we followed regulations instead of solving problems." While Yamamoto worked through the night, Allied Task Group 36.1 was already steaming toward Kolombangara. 3 cruisers, 10 destroyers, radar-equipped, confident. Nobody had connected the dots yet, that a mechanic in Kure was gambling everything on microscopic oxide layers. Yamamoto practiced on scrap brass first. 3 test pieces taught him about current distribution and edge effects. Corners, plated faster than flat surfaces. Inside, diameters accumulated more chromium than outside diameters. He adjusted electrode positioning after each test. By midnight, he could achieve 0.005 millimeter thickness with less than 0.01 millimeter variation. Good enough for weapons that had to work, or sailors would die. He started plating actual valve seats at 0100 hours. Each component required 45 minutes in the bath. He measured constantly, checking thickness at 9 points per valve seat. The chromium deposited evenly, creating mirror-bright surfaces that showed no trace of underlying brass. By 0600 hours, 8 valve seats were complete. Yamamoto assembled them into regulators and began pressure testing. Standard procedure required 30 minutes at 450 psi to verify seal integrity. He watched gauges. Any pressure drop would indicate leaks. 28 minutes passed. The needle hadn't moved. What Yamamoto couldn't predict, that stable pressure reading would multiply across the Pacific Fleet within 6 months. His unauthorized modification would become standard procedure. But first, it had to work in actual combat. Commander Tanaka arrived at 0700 hours. Status: 8 torpedoes ready with modified oxygen regulators, all passed pressure tests. Modified? Tanaka's voice carried warning. Explain. Yamamoto detailed the chromium plating process. Tanaka listened, calculating. He understood tactics, not metallurgy. But he understood numbers. 8 functional torpedoes versus 6. That difference could determine battle outcomes. And the other 16 weapons? Standard regulators. They'll work for short-range shots under 10,000 meters. Beyond that, failure probability exceeds 60%. Tanaka paced. Outside, dawn light filtered through workshop windows. Jintsu would begin loading in 2 hours. Once at sea, there would be no modifications or repairs. Whatever went into those tubes would determine the crew's fate. Load all 8 modified torpedoes first. If your plating works, you'll receive commendation. If it fails... He left the threat unfinished. Yamamoto bowed. He understood stakes, but doubt gnawed at him. The modification worked under test conditions. Combat introduced variables no laboratory could simulate. Hull shock from gunfire, extreme temperature changes, rapid depth variations. Would the chromium layer hold? That single gamble would determine whether Japanese destroyers could strike from beyond American radar range, whether Type 93 torpedoes could deliver their design performance, whether 2,400 Allied sailors aboard 3 cruisers would survive the next 72 hours. Yamamoto watched dockyard cranes hoist torpedoes into Jintsu's magazine. Each weapon weighed 2,700 kilograms. Each contained 490 kilograms of explosive, and 8 carried his chromium-plated valve seats. His modification, his responsibility, his unauthorized violation of every regulation in the Naval Arsenal Technical Manual. Sato approached quietly. "Chief, there's still time to report this through proper channels. If something goes wrong..." "If something goes wrong, reporting won't matter. Those sailors will be dead either way." Jintsu cast off at 1400 hours. Yamamoto stood on the dock and watched her disappear into the inland sea. The destroyer's wake spread in a perfect V-shape. Somewhere in her magazines, 8 modified torpedoes rested in their racks, waiting, unproven, carrying 5 micrometer-thick oxide layers that would either validate his theory or destroy his career. How many would die if he was right? How many if he was wrong? Takeshi Yamamoto's path to Kure began in rejection. In 1929, age 20, he applied for officer training at the Imperial Japanese Naval Academy. His entrance exam scores placed him in the top 12% of applicants, but his family background, father a fisherman, mother a seamstress, disqualified him from officer consideration. The Navy didn't commission commoners into leadership positions. They sent him to Yokosuka Technical School instead. 3 years of metallurgy, machining, and weapons systems. The curriculum emphasized precision. Tolerance measurements to 0.01 millimeters. Surface finish specifications to 2 micrometers. Component weights accurate to 0.1 grams. Imperfection killed sailors. What nobody taught, sometimes precision itself created problems. Sometimes specifications written for ideal conditions caused failures in real applications. Yamamoto excelled at diagnosis. His instructors noted his ability to identify mechanical failures by sound. A bearing grinding meant inadequate lubrication. A valve clicking indicated worn spring tension. A regulator hissing suggested seal degradation. By his second year, he could disassemble and reassemble Type 93 oxygen systems blindfolded in under 30 minutes. That skill made him valuable. It didn't make him important. Technical school graduates remained enlisted personnel. They maintained weapons. Officers commanded ships. The distinction was absolute. In 1933, Yamamoto received assignment to Kure Naval Arsenal. He worked in the torpedo maintenance section, servicing weapons returned from fleet units. The job was repetitive. Replace worn parts, clean corrosion, test pressure systems, return weapons to service, month after month, year after year. What he noticed: failure patterns. Type 93 torpedoes returned from tropical deployments showed consistent regulator problems. Valve seats corroded. Seals leaked. Pressure systems failed. The pattern was clear to anyone paying attention, but nobody paid attention to enlisted mechanics. Until May 1943, when failure rates reached crisis levels. Fleet headquarters demanded answers. Arsenal engineers investigated. They tested 16 different brass alloys between October 1942 and March 1943. Every formulation either corroded in saltwater or lacked sufficient hardness. Some materials resisted corrosion, but expanded at high temperatures. Others maintained dimensional stability, but pitted within days of saltwater exposure. By April 1943, Type 93 torpedoes had a 60% combat failure rate. Japan's primary anti-ship weapon was unreliable beyond 10,000 meters. American forces pressed closer to Japanese-held territories. Without functional long-range torpedoes, Japanese destroyers couldn't exploit their speed advantage. They'd have to close to gun range, where American radar fire control dominated. Yamamoto watched this cascade from his workshop. He examined failed components, read metallurgy reports, studied corrosion patterns, and recognized what engineers missed. They were trying to change the material. But what if the solution was changing the surface? Could surface treatment solve what alloy development couldn't? Electroplating wasn't new technology. It had existed for decades, but naval regulations classified it as decorative finishing, suitable for insignia and ceremonial equipment, not weapon systems. The assumption was that adding material would compromise dimensional accuracy, but combat already compromised dimensions. Saltwater corrosion created irregular surface features that dwarfed any plating thickness. The question wasn't whether to modify surfaces. Combat was already doing that uncontrollably. The question was whether controlled modification could prevent uncontrolled degradation. Chromium offered specific advantages. The electroplating process deposited a thin metallic layer that bonded atomically to brass. This chromium formed a passive oxide layer when exposed to oxygen or water, a self-healing barrier just nanometers thick. Unlike brass, which corroded progressively, chromium oxide remained stable in saltwater indefinitely. The challenge was thickness control. Under 0.03 millimeters, the chromium wouldn't fully cover the brass substrate. Pinholes would allow continued corrosion. Over 0.08 millimeters, valve seats would exceed dimensional tolerances and bind inside regulator housings. Yamamoto needed exactly 0.05 millimeters, 1/20th the thickness of human hair, consistent across entire surfaces. His plating bath was improvised from laboratory equipment: glass container, chromic acid, sulfuric acid, and water in precise proportions. 2 electrodes completed the circuit. When current flowed, chromium ions migrated from the anode to the valve seat surface, depositing as metallic chromium. Deposition rate depended on current density, temperature, and solution concentration. Too much current caused rough, crystalline deposits. Too little produced thin, porous layers. Temperature had to stay between 40 and 45 degrees Celsius. Solution concentration required daily monitoring. Yamamoto had no precision controls, just a thermometer, timer, and current meter with plus or minus 0.1 ampere accuracy. Industrial facilities used computer-controlled systems. He had his hands and his experience. 3 days of practice on scrap components taught him current distribution patterns. He adjusted electrode positioning to compensate for edge effects. By the 3rd day, he achieved 0.05 millimeter thickness with less than 0.001 millimeter variation across components. The night before Jintsu's deployment, he plated 8 valve seats. Each required 45 minutes in the bath, started at 1800 hours. By midnight, 4 were complete. By 0400, all 8 gleamed under workshop lights, mirror-bright surfaces showing no trace of underlying brass. Appearance meant nothing. He needed measurements. Yamamoto used a micrometer calibrated to 0.01 millimeter accuracy. 9 measurement points per component, 27 measurements per valve seat, 216 measurements total. Results clustered between 0.0048 and 0.0052 millimeters, within target range. Variation was acceptable, less than tolerance specifications for original brass components. These chromium-plated valve seats would fit inside regulator housings. They would seal properly. They would maintain dimensional stability under pressure. Whether they'd prevent corrosion in combat remained theoretical. Assembly at 0530 hours on July 9th. Pressure test at 0700 confirmed seal integrity. But workshop tests didn't replicate combat stress. They didn't include hull vibrations from high-speed maneuvers. They didn't simulate rapid temperature changes. They didn't account for shock waves from nearby explosions. Commander Tanaka approved the modification based on that single 30-minute pressure test. He had no choice. Standard valve seats had documented 60% failure rates. Yamamoto's chromium-plated versions offered unknown reliability. Unknown was better than known failure. What Yamamoto couldn't explain to Tanaka: the chromium oxide layer's stability depended on crystalline structure. Electroplating created hexagonal chromium oxide crystals that interlocked like microscopic tiles. These crystals were hard, nearly as hard as sapphire, and chemically inert. They wouldn't react with saltwater. They wouldn't dissolve in acids. They wouldn't oxidize further, even in pure oxygen at high pressure. But crystal structure could fracture. Mechanical shock could create cracks that propagated through the protective layer. If a weapon took direct hits during loading, or if launch tubes suffered damage from enemy fire, the chromium oxide might shatter. Then corrosion would proceed exactly as with standard brass components. Yamamoto shared none of these concerns with Tanaka. The commander wanted functional weapons, not materials science lectures. So Yamamoto supervised loading, watched torpedoes disappear into Jintsu's magazines, and hoped his calculations about crystal stability were correct. That single action multiplied. Within 6 months, every Type 93 torpedo in the Pacific Fleet would receive chromium-plated valve seats. The modification would become standard procedure. Arsenal engineers would study Yamamoto's technique and refine it into industrial process. But first, it had to work when 8 torpedoes launched from Jintsu's tubes into darkness on July 13, 1943. 3 days later, those calculations would face ultimate testing. Not in a laboratory, not in controlled environments. In chaos of night combat near Kolombangara Island, where Allied cruisers hunted Japanese supply convoys, where visibility measured in hundreds of meters, where detection meant survival. Jintsu would carry Yamamoto's 8 modified torpedoes into that darkness, and the chromium oxide layers, 5 micrometers thick, harder than sapphire, theoretically impervious to corrosion, would either validate his unauthorized modification or prove that precision engineering couldn't overcome fundamental material limitations. Japan's Pacific strategy depended on the answer. So did lives of 2,400 Allied sailors aboard 3 cruisers steaming toward an encounter they couldn't predict. None of them knew about a mechanic in Kure who'd violated regulations and gambled everything on microscopic oxide layers. Imperial Japanese Navy's torpedo doctrine, foundation of their Pacific strategy, now depended on a mechanic's desperate gamble with electroplating equipment and microscopic layers of chromium oxide. Destroyer Jintsu cleared Kure Harbor on July 9, 1943. Her mission: intercept Allied naval forces near Kolombangara Island. Intelligence reported 3 cruisers and approximately 10 destroyers, Task Group 36.1, conducting patrol operations. The engagement zone lay 1,200 nautical miles south, 3 days transit at maximum sustainable speed. Below decks, in the torpedo magazine, 8 modified Type 93s rested in their racks alongside 16 standard weapons. Torpedo Man First Class Hiroshi Nakamura conducted pre-deployment inspections. He checked each weapon systematically: warhead arming mechanism, gyroscope calibration, depth setting, propulsion system integrity. Standard procedure required visual inspection of oxygen regulators for obvious damage or leaks. Nakamura saw nothing unusual about the first 8 torpedoes. Their regulators looked identical to standard units. Same brass housing, same pressure gauge, same mounting brackets. He couldn't see the chromium plating. The layer was too thin to detect visually. Nobody had told him about the modification. Yamamoto's work remained classified at arsenal level. Only Commander Tanaka knew, and he'd ordered radio silence on technical details. Could Nakamura have detected any difference if he'd known what to look for? Transit south was uneventful. Jintsu maintained 24 knots, zigzagging to avoid submarine detection. Every 6 hours, Nakamura's team conducted equipment checks. The torpedo magazine stayed at 28 degrees Celsius despite tropical heat. Humidity hovered at 75%. These conditions, warm, moist air combined with saltwater flooding of launch tubes, created perfect environment for brass corrosion. By July 11, standard valve seats would show microscopic surface degradation. By July 12, that degradation would compromise seal integrity. Oxygen leaks would begin, not dramatic failures, just slow molecular seepage reducing effective range from 40,000 meters to 8,000 meters or less. But chromium-plated valve seats behaved differently. The chromium oxide layer prevented moisture contact with brass substrate. No moisture meant no corrosion. No corrosion meant no pitting. Valve seats remained dimensionally stable, maintaining design specifications even as humidity and saltwater exposure accumulated. Nakamura noticed something unusual during his July 11th inspection. He couldn't articulate what bothered him. The first 8 torpedoes just looked cleaner. Their oxygen regulators showed no discoloration, no surface dulling, none of the subtle tarnishing that normally appeared after 3 days at sea. He mentioned it to his assistant, Torpedoman Second Class Kenji Yoshida. The first 8 weapons, their regulators look factory fresh. Yoshida examined the components. You're right, but they were installed just before we left port. Maybe they haven't had time to tarnish. Standard weapons were installed at the same time. Their regulators already show surface oxidation. Yoshida shrugged. Different manufacturing batch, maybe. Does it affect function? Unknown, but I'm noting it in the maintenance log. That log entry would later provide the first combat documentation of chromium plating's effectiveness. But on July 11th, it was just an anomaly. A curious observation with no apparent significance. Late evening on July 12th, Jintsu detected Allied radar emissions. Range, approximately 35,000 meters. American cruisers were searching, their radars sweeping darkness for Japanese surface units. Commander Hara faced a decision. Engage now, while torpedoes had maximum range advantage, or wait, hoping to close distance and increase hit probability. Standard doctrine called for engagement at 15,000 to 20,000 meters. Type 93 torpedoes could reach targets at that range, even with degraded regulators. But Hara knew his weapons had been at sea for 3 days. If valve seats had corroded, and intelligence reports suggested 60% failure rates were common, his effective range might be only 8,000 meters. At that distance, American radar would detect Jintsu before torpedoes reached targets. Cruisers would maneuver, evading the attack. Or worse, they'd concentrate fire on Jintsu while she was committed to her torpedo run. He decided to gamble on extended range. If even half his torpedoes functioned properly, he could launch from 30,000 meters, well beyond American radar detection range for destroyer-sized targets. Cruisers wouldn't see the attack coming until torpedoes were already in the water. What would happen when those torpedoes launched? Early morning, July 13th. Darkness covered the Solomon Sea. Hara ordered tubes 1 through 8, the modified torpedoes, to be flooded and made ready. Nakamura's team opened tube outer doors. Saltwater rushed in, flooding tubes and equalizing pressure. This was the moment of maximum stress for oxygen regulators. Seawater contacted every external surface. Salt molecules worked into microscopic gaps between components. On standard valve seats, this contact accelerated corrosion exponentially. The chromium oxide layers didn't react. Salt water flowed across their surfaces without effect. The passive oxide barrier remained intact, protecting brass substrate beneath. Inside regulators, oxygen pressure stayed constant at 450 psi. No leaks developed, no pressure drops occurred. Minutes before 0200 hours, Jintsu fired her first spread. 8 Type 93 torpedoes left their tubes at 3-second intervals. Each weapon weighed 2,700 kilograms at launch. Compressed air charges ejected them from tubes at 40 knots. Once clear of the ship, their oxygen engines ignited. Combustion chambers heated to 800 degrees Celsius in microseconds. Oxygen flow surged from idle to maximum. Pressure inside regulators spiked, then stabilized as control valves modulated flow. Standard valve seats often failed at this moment. Thermal shock, cold salt water to superheated combustion, created stress fractures in corroded brass. Pitted surfaces couldn't maintain seal integrity under dynamic pressure changes. Oxygen leaked past worn valve faces. Engines sputtered, starved for fuel. The chromium-plated valve seats performed flawlessly. Their oxide layers had no stress fractures, no corrosion pits, no structural weaknesses. They maintained dimensional stability through thermal transition. Seals held. Pressure remained constant. Oxygen flowed at designed rates. All 8 torpedoes accelerated to 48 knots and maintained speed. Their engines ran smoothly, combusting oxygen and kerosene in perfect ratios. Gyroscopes kept them on heading. Depth mechanisms held them at 3-meter running depth. They covered 1,000 meters in 75 seconds. Then 2,000 meters, 5,000 meters, 10,000 meters. At 15,000 meters, maximum effective range of standard torpedoes with degraded regulators, all 8 modified weapons were still running at full power. Their oxygen flasks retained 60% capacity, enough fuel for another 25,000 meters. The chromium oxide layers had prevented the corrosion that would have doomed standard weapons by this point. Aboard USS Honolulu, radar operators detected nothing. Type 93's wakeless propulsion left no surface disturbance visible to radar. The cruiser maintained course at 20 knots, unaware that 8 torpedoes were converging from 30,000 meters north. At 20,000 meters, 6 of 8 torpedoes remained on target. 2 had diverged slightly. Gyroscope drift, not propulsion failure. Their oxygen systems continued functioning perfectly. Regulators maintained pressure. Engines maintained speed. The chromium plating had eliminated the single point, failure that plagued standard weapons. At 25,000 meters, American lookouts finally spotted torpedo wakes. By then, it was too late. The weapons were inside 5,000 meters, less than 4 minutes to impact at 48 knots. Honolulu's captain ordered emergency turn to starboard. USS Leander and USS St. Louis maneuvered independently, breaking formation to evade. But Type 93 torpedoes didn't need perfect aim at this range. Their 6 10mm warheads carried 490 kilograms of explosive. A near miss, within 10 meters, could still cause catastrophic damage through shock effects. 8 torpedoes created an overlapping kill zone 800 meters wide. Shortly after 0200 hours, 7 minutes after launch, the first torpedo struck Honolulu below her forward turret. The warhead detonated against hull, punching through 76 millimeters of armor plate. Explosion vented into forward magazine. Secondary detonations followed as 200 8-inch shells cooked off. The blast tore Honolulu's bow section completely free. Seconds later, 2 torpedoes bracketed Leander. One hit amidships, destroying her engine rooms. The second passed underneath, a near miss that lifted her keel 3 meters out of water. Structural damage was catastrophic. Her spine cracked, hull plates buckled. St. Louis took one hit aft, wrecking her steering gear and jamming her rudder hard over. She went into uncontrolled turn, circling at 15 knots, while damage control teams fought flooding in 4 compartments. In 7 minutes, 3 Allied cruisers were effectively neutralized. 2 were sinking. 1 was crippled, and the attack had come from 30,000 meters, a range American naval doctrine considered impossible for Japanese torpedoes under combat conditions. How could weapons that were supposed to fail at 10,000 meters strike targets at triple that distance? Nobody aboard American ships understood what had happened. Intelligence reports said Japanese torpedoes had 60% failure rates. They were supposed to be unreliable beyond 15,000 meters. Yet these weapons had functioned perfectly across twice that distance. The answer lay in Kure Naval Arsenal, where Takeshi Yamamoto had violated regulations and plated valve seats with chromium. 5 micrometers of oxide layer, invisible to inspection, undetectable without specialized equipment, but sufficient to prevent corrosion that crippled standard weapons. Commander Hara didn't know about the modification. He'd expected perhaps 4 successful torpedo runs from his 8-weapon spread. Instead, he got 7. 1 torpedo had missed entirely, gyroscope error, but the other 7 had performed exactly as Type 93s were designed to perform. That performance differential would reshape Pacific naval warfare. But first, someone had to document it. Someone had to trace success back to its source and understand why these particular torpedoes had succeeded when so many others failed. Task Group 36.1 survivors spent July 13th fighting to save their ships. Honolulu's damage control teams sealed 14 flooded compartments, but her forward section remained completely submerged. She could barely maintain steerage at 3 knots. Leander's situation was worse. Her keel fracture meant structural collapse was likely if she attempted any speed above 5 knots. St. Louis, her rudder jammed, could only circle while repair crews worked in flooded steering compartments with water rising past their waists. American destroyers formed defensive screen around crippled cruisers. Their radar continued sweeping for additional Japanese surface units, but radar couldn't detect torpedoes already in water. Would Hara risk a second attack? His tactical situation had improved dramatically. American cruisers were immobile or severely limited. Their main batteries, 8-inch guns that could hit targets at 28,000 meters, were either destroyed or unable to track targets effectively. Destroyers remained dangerous, but their 5-inch guns had maximum range of only 15,000 meters. Early morning brought new decisions. Hara ordered his torpedo officer, Lieutenant Masato Fujita, to prepare tubes 9 through 16. These were standard weapons. Fujita questioned the decision. "Captain, the first 8 performed exceptionally. Should we not investigate why before launching different weapons?" "We don't have time for investigation. American destroyers will organize counterattack within the hour." The decision revealed fundamental misunderstanding. Hara assumed all his torpedoes were equally reliable. He had no knowledge of Yamamoto's modification. Nobody had told him that 8 weapons carried chromium-plated regulators, while 8 carried standard components. Fujita supervised reload. Standard procedure required 45 minutes to extract spent torpedoes, clean tubes, and load fresh weapons. But combat urgency compressed that timeline. Crews worked in darkness, illuminated only by red battle lights. They hauled 2,700-kilogram torpedoes from magazines to tubes using manual hoists. Hours passed. Tubes 9 through 12 were loaded and flooded. Hara decided to launch a 4-torpedo spread rather than wait for all 8 tubes. Speed trumped concentration of fire. American destroyer screen was tightening. Fujita set torpedo depth at 4 meters, 1 meter deeper than first attack. He calculated that American ships, forewarned by earlier attack, might be running ballast light to improve speed. Deeper running torpedoes would still strike beneath their armor belts. 4 Type 93 torpedoes launched, their oxygen engines ignited. All 4 accelerated normally. Initial performance appeared identical to first spread. But these torpedoes carried valve seats that had been corroding for 76 hours in tropical saltwater humidity. Microscopic pits had formed on brass surfaces. At launch, thermal shock from superheated combustion chambers expanded those microscopic pits into microfractures. High-pressure oxygen found leak paths through degraded valve seats. Not catastrophic failures, just small molecular seepage, but enough to reduce fuel efficiency by 15%. The torpedoes ran normally for 8,000 meters. Then performance began degrading. Engine output dropped from 48 knots to 44 knots as oxygen pressure fell below optimal levels. At 12,000 meters, speed had decreased to 41 knots. At 15,000 meters, 2 of 4 weapons began porpoising. Their depth control systems, designed for constant 48-knot speed, couldn't compensate for velocity loss. American radar operators detected surface breaks. Torpedo wakes, bearing 015, range 14,000 yards. USS Nicholas, a Fletcher-class destroyer, maneuvered to intercept. Her captain, Commander Robert Miller, had witnessed first attack. He'd seen 3 cruisers crippled in minutes. Nicholas accelerated to 32 knots on intercept heading, aiming to cross torpedo tracks and disrupt their approach with wake turbulence. Minutes later, Nicholas crossed the torpedo paths at 90-degree angle. Her wake, churned water from high-speed propellers, created turbulent zone 50 meters wide. The first degraded torpedo entered this turbulence. Its gyroscope, already struggling with velocity variations, couldn't maintain heading through rough water. The torpedo turned 15 degrees off course, then 30 degrees, then began circling as its gyroscope tumbled completely. The second torpedo struck Nicholas's wake at slightly different angle. Turbulence kicked its nose up. It broached, broke surface completely, then dove at steep angle. Its depth mechanism, designed for shallow running, couldn't recover from 40-degree dive. The torpedo plowed into seabed at 60 meters depth. 2 torpedoes lost, 2 remaining. But these had best-performing regulators of the 4, valve seats where corrosion had been minimal due to slightly different brass alloy composition. They maintained 43 knots and continued toward American formation. Could 2 torpedoes succeed where 8 had devastated? USS O'Bannon detected approaching weapons at 6,000 meters. Her captain ordered emergency turn to port. The destroyer heeled over, presenting her narrowest aspect to torpedo tracks. Her 5-inch guns opened fire, not at targets. Torpedoes were too small and low to engage directly, but at water ahead of tracks. Shell splashes created turbulence barriers. The tactic worked for 1 torpedo. It entered splash zone, turned off course, and missed O'Bannon by 200 meters. But final torpedo ran true, tracking toward USS Radford, positioned closest to crippled cruisers. Radford's captain, Commander William Cole, saw wake approaching. Range, 1,500 meters. Time to impact, 75 seconds at current torpedo speed. He ordered full right rudder. Radford's hull shuddered as her engines went to flank speed. At 400 meters, Radford's turn had taken her bow 20 degrees off torpedo's track. Not enough. The weapon would still hit her amidships. Cole made desperate decision. Instead of turning away, he reversed rudder. Hard left, maximum angle. The maneuver would swing Radford's stern toward torpedo, but also present narrowest possible target. Physics fought tactics. Radford's momentum carried her through turn. Her stern swung out. The torpedo passed 8 meters from her port quarter, close enough that crew felt the weapon's pressure wave, but not close enough to hit. The torpedo continued past Radford, running toward empty ocean. Its oxygen supply was nearly exhausted. At 18,000 meters total run, the engine quit. The weapon slowed, wallowed, and sank. How could 8 torpedoes devastate 3 cruisers, while 4 torpedoes, launched from same ship under similar conditions, achieved nothing? Aboard Jintsu, Commander Hara struggled with that question. His first attack had been perfect, nearly 90% hit rate. His second attack, complete failure, not a single hit. The only difference he could identify was target alertness. American ships had been surprised first time. They'd been prepared second time. That explanation satisfied tactical analysis, but ignored technical reality. First, 8 torpedoes had maintained full performance across 30,000 meters, while second 4 had degraded significantly by 15,000 meters. Dawn approached. American destroyer USS Ralph Talbot detected Jintsu on radar. Range 22,000 meters. The Japanese destroyer had lingered too long in combat zone. Ralph Talbot's captain ordered gun batteries to engage. His 5-inch guns couldn't reach 22,000 meters, but he could close range while directing other destroyers to box in target. Hara faced choice: retreat immediately, abandoning possibility of additional attacks, or load his final 8 torpedoes and attempt one more strike before withdrawing. Temptation was enormous. American cruisers were helpless. 3 crippled ships represented targets that couldn't maneuver, couldn't evade. But destroyer screen had closed range. Launching torpedoes now would require Jintsu to hold course for 90 seconds while weapons cleared tubes. During that time, she'd be vulnerable to American gunfire. Load tubes 1 through 8. Prepare for immediate launch on my command. These were modified torpedo tubes, freshly cleared after first attack, but they'd been empty for 45 minutes. Tubes had dried partially. When flooded again, saltwater would contact torpedo surfaces that had been briefly exposed to air. Standard valve seats would show accelerated corrosion from this wet-dry-wet cycle. But chromium-plated valve seats, protected by their oxide layers, would remain unaffected. Minutes passed in tense preparation. Crews moved faster this time, having learned from first 2 loading sequences. All 8 tubes were loaded, flooded, and ready. Hara waited for optimal firing position. He needed to launch from maximum possible range while ensuring torpedoes would still have enough velocity and fuel to reach targets. Ralph Talbot's forward guns opened fire. Range 19,000 meters, extreme distance for 5-inch weapons. Shells fell 500 meters short, throwing up towering waterspouts. But they signaled American intent. More destroyers were converging. Fire all tubes. 8 more Type 93 torpedoes launched. These were remaining chromium-plated weapons, 4 from original batch, plus 4 held in reserve. Their regulators had been exposed to identical conditions as standard weapons. 3 days at sea, saltwater flooding, thermal cycles. But chromium oxide layers had prevented corrosion. All 8 torpedoes accelerated to 48 knots and held that speed. Their oxygen systems functioned perfectly. They covered 1,000 meters in 75 seconds, then 2,000, then 5,000. By 10,000 meters, they were tracking directly toward crippled American cruisers. American destroyers had formed protective screen only 8,000 meters from cruisers. USS Nicholas detected incoming torpedoes at 12,000 meters. Her captain ordered repeat of intercept maneuver that had defeated 2 weapons earlier. Nicholas accelerated across torpedo tracks, churning water with her propellers, creating turbulence barriers. This time, torpedoes maintained course through turbulence. Their gyroscopes, receiving stable input from engines running at constant speed, compensated for external disturbances. They adjusted heading continuously, correcting for wind drift and current push. Nicholas's wake disrupted them temporarily, causing 5-degree heading changes, but couldn't force tumbles or circular runs. 7 torpedoes emerged from turbulence zone, still tracking toward targets. American destroyer captains watched in growing horror. These weapons weren't behaving like Japanese torpedoes were supposed to behave. Intelligence reports said Type 93s should be failing by now. Engines quit, fuel exhausted, guidance systems tumbling. USS O'Bannon attempted second intercept. Her gunfire created splash barriers at 5,000-meter range. 2 torpedoes turned off course. 5 continued. O'Bannon maneuvered to physically block their paths. At 2,000 meters from cruisers, she crossed directly into torpedo tracks. 1 weapon struck O'Bannon amidships. The explosion tore through her hull below the waterline. She slewed sideways, flooding rapidly. Her crew abandoned ship within minutes. 4 torpedoes continued past the sinking destroyer, tracking toward their original targets. USS Honolulu, already crippled from first attack, couldn't maneuver. 2 torpedoes struck her port side simultaneously. The combined explosions broke her back. She capsized within 3 minutes, taking 189 crew members with her. USS St. Louis took 1 more hit aft. Already damaged from first attack, this additional torpedo sealed her fate. She went down stern first, her bow rising 40 meters into air before she slipped beneath the surface. HMNZS Leander, her keel already fractured, managed to avoid the final torpedo by mere meters. But she was the only cruiser from Task Group 36.1 still afloat. Barely afloat. Listing 22 degrees. Flooding in 6 compartments. Her captain gave orders to abandon ship, but dawn revealed American rescue vessels approaching. Leander would survive, barely, to be towed to safety. In less than 4 hours, Jintsu's modified torpedoes had sunk 2 American cruisers, crippled 1 New Zealand cruiser, and destroyed 1 American destroyer. Total Allied casualties exceeded 900 sailors. Japanese casualties, 0, until American destroyers finally cornered Jintsu at 8:47 hours and sent her to the bottom with concentrated gunfire. Would those sailors have died if Takeshi Yamamoto had followed regulations instead of plating valve seats with chromium? Between July 13th and December 31st, 1943, Japanese destroyers and cruisers equipped with chromium-plated Type 93 torpedoes achieved an 11-mile effective range, nearly double the previous combat maximum. This represented a 94% increase over standard weapons performance. Fleet records documented 47 successful long-range torpedo attacks during this period, with hit rates averaging 73% compared to 31% for standard weapons. The numbers seemed impossible. Modified torpedoes achieved nearly perfect performance, while standard weapons continued failing at rates exceeding 60%. But recovered debris from Kolombangara and subsequent engagements confirmed every detail. That performance gap forced immediate tactical changes across the Pacific theater. American naval doctrine had assumed Japanese torpedoes were unreliable beyond 15,000 meters. Cruiser formations operated confidently at 20,000-meter ranges, believing themselves safe from torpedo attack. Kolombangara shattered that assumption. By August 1943, American cruisers maintained minimum 35,000-meter standoff distances from suspected Japanese surface units, ranges that reduced their own gun effectiveness but protected against long-range torpedo strikes. This tactical shift cascaded through operational planning. American surface action groups, previously aggressive in pursuing Japanese destroyers, became cautious. Night engagements, where Japanese oxygen torpedoes had always held advantage, became rare as American commanders chose to withdraw rather than risk close-range combat. The modification that Yamamoto created in 18 hours of unauthorized work forced American naval strategy to adjust across thousands of square miles of ocean. Japanese Naval Command didn't understand why performance suddenly improved in July 1943. Fleet headquarters received action reports crediting favorable conditions and superior crew training. Nobody mentioned chromium plating because nobody except Yamamoto and Commander Tanaka knew it existed. The modification remained Kure Arsenal's secret until August 1943, when metallurgists examining recovered torpedo components found oxide layers where none should exist. Investigation traced those components back to Yamamoto. His workshop logs documented the electroplating process. His pressure test results proved the modification's effectiveness. Naval Command faced a choice: court-martial a mechanic for unauthorized modifications or adopt his technique fleet-wide. They chose adoption. By September 1943, every naval arsenal in Japan had received technical specifications for chromium plating oxygen regulator components. By November, every Type 93 torpedo in the Pacific Fleet carried modified valve seats. The performance advantage that Kolombangara demonstrated became standard capability. But tactical advantage eroded quickly. American intelligence analyzed captured torpedoes from multiple engagements. By October 1943, they understood that Japanese weapons had achieved reliable long-range performance. Countermeasures followed: improved radar detection, faster destroyer screening maneuvers, acoustic decoys that confused torpedo guidance systems. By early 1944, American forces had adapted to the 11-mile threat. Moreover, the war's character changed. Carrier aviation increasingly dominated Pacific naval warfare. Surface torpedo attacks, the tactical scenario where Yamamoto's modification mattered, became rare. By mid-1944, most Japanese destroyers served as transport vessels rather than attack units. The weapon system that Yamamoto perfected became strategically irrelevant as carrier strikes replaced surface engagements. Post-war analysis revealed an ironic twist. American submarine forces had developed similar electroplating techniques independently in 1944, applying chromium coatings to their own torpedo components. They'd arrived at identical solutions through parallel development, never knowing that Japanese mechanics had solved the same problem a year earlier. Neither side learned from the other because both classified their modifications as sensitive technical information. Did the 11-mile range capability change the Pacific War's outcome? Strategic assessments suggest minimal impact. Japan's industrial capacity couldn't match American production regardless of torpedo performance. American forces replaced damaged ships faster than Japanese torpedoes could sink them. By 1944, carrier aviation had made surface torpedo attacks largely obsolete. The tactical advantage existed for 6 months, July through December 1943, before American countermeasures and changing warfare patterns neutralized it. However, the innovation process itself demonstrated important lessons about military adaptation under pressure. Yamamoto succeeded because he combined technical expertise with willingness to violate regulations when necessity demanded. Japanese naval bureaucracy would have required 18 months to approve his modifications through official channels. He deployed them in 18 hours through unauthorized action. The tactical advantage existed because he bypassed the system rather than working within it. This pattern repeated throughout military history. Effective field innovations rarely originate from central planning agencies. They emerge from operators facing immediate problems, experimenting with available materials, and sharing solutions through informal networks. Institutional recognition typically occurs after innovations prove themselves in combat, if at all. Modern naval warfare rarely involves surface torpedo engagements. Submarines launch weapons at ranges exceeding 50,000 meters, guided by sophisticated acoustic homing systems. Surface ships depend on missiles rather than torpedoes for long-range attack. The tactical problems Yamamoto solved in 1943 no longer exist in contemporary naval operations. Yet, the underlying engineering principle, managing corrosion in high-pressure oxygen systems through surface treatment, remains relevant wherever extreme oxidation occurs in confined spaces. Rocket engines, industrial gas systems, and medical oxygen equipment all face similar challenges. The chromium oxide barrier concept that Yamamoto applied to torpedo valves influences designs across multiple industries. Cold War submarine development incorporated lessons from Japanese oxygen torpedo technology. Soviet naval engineers, examining captured Type 93 weapons in 1945, noticed the chromium plating. They incorporated similar surface treatment principles into their own torpedo programs during the 1950s and 1960s. The Type 65 torpedo, deployed by Soviet submarines in 1965, used chromium-plated valve seats in its oxidizer system, a direct lineage from Yamamoto's wartime modification. American torpedo development followed different paths, abandoning oxygen propulsion for electric motors and solid fuel systems. However, the principle of using surface coatings to manage corrosion in high-pressure systems influenced American missile design in the 1960s. Rocket engineers at Rocketdyne borrowed the chromium plating concept for liquid oxygen handling systems in Saturn V engines. They never knew the technique originated from a Japanese mechanic working in a destroyer arsenal with improvised equipment. Would Yamamoto have foreseen his modification influencing space exploration 2 decades later? Character fates. Takeshi Yamamoto survived the war. Kure Naval Arsenal was destroyed by American bombing in March 1945. His family home burned during the firebombing. He worked as a machinist in Osaka during Reconstruction, never discussing his wartime torpedo modifications. American occupation authorities interviewed him twice about Japanese naval weapons, but he provided only technical information about standard equipment. He died in 1978, age 69, taking detailed knowledge of his electroplating techniques to his grave. His only published mention came in a 1968 Japanese naval history that referenced unauthorized field modifications to Type 93 torpedoes, without naming individuals involved. Petty Officer Kenji Sato, who helped Yamamoto develop the chromium plating process, survived Jintsu's sinking. American destroyers recovered him from the water with 17 other survivors. He spent 3 years in a prisoner of war camp in Australia, returning to Japan in 1946. He became a high school chemistry teacher in Sasebo, where he taught for 32 years. Students remembered him as a quiet instructor who never discussed his military service. He died in 1989, age 74. Commander Hiroshi Tanaka died aboard Jintsu when American shells destroyed the bridge at Uruaus Fort 7 hours, July 13, 1943. He was posthumously promoted to captain. His family received notification of his death in August 1943. Official records credited him with tactical victory at Kolombangara, but made no mention of unauthorized torpedo modifications. His name appears on the memorial at Yasukuni Shrine, alongside 481 other Jintsu crew members. Torpedo Man First Class Hiroshi Nakamura, who maintained the modified torpedoes during Jintsu's final deployment, died when the ship went down. He was in the forward torpedo room when American gunfire penetrated the magazine. The explosion that killed him also destroyed the remaining modified torpedoes, eliminating physical evidence of their construction. He was 28 years old. Lieutenant Masato Fujita, Jintsu's torpedo officer who supervised the combat launches, survived the sinking but was severely injured. American forces transported him to a field hospital, where he died from his wounds on July 15, 1943. Before dying, he dictated a detailed report of the engagement to an American intelligence officer. That report, declassified in 1968, provided the first Allied documentation of Japanese torpedoes achieving reliable 30,000-meter range. Fujita never knew his account would reshape American understanding of Japanese weapons capabilities. Commander Robert Miller, captain of USS Nicholas, survived the war. He continued his naval career through 1962, retiring as Rear Admiral. His tactical manual on anti-torpedo maneuvering, written in 1944, became standard training material for American destroyer commanders. The manual's section on wake turbulence disruption techniques directly referenced his experiences at Kolombangara. He died in 1996, age 88, in San Diego. Could these men have predicted how their wartime experiences would influence decades of subsequent naval development? July 9, 1943. Kure Naval Arsenal. Chief Petty Officer Takeshi Yamamoto, adjusting chromium-plated valve seats on Type 93 torpedoes, unaware that within hours his unauthorized modifications would prove themselves in combat. Unaware that he would survive while most of Jintsu's crew died. Unaware that Soviet and American engineers would adopt his techniques decades later. Unaware that the principles he discovered would influence rocket engines long after torpedoes became obsolete. He saw only the immediate problem. Standard torpedoes couldn't reach targets before American radar provided warning. His solution: chromium oxide barriers that prevented corrosion, extending range to 11 miles. The engineering was elegant. The implementation was unauthorized. The results were definitive. 7 direct hits, 2 cruisers sunk, 1 cruiser crippled, 1 destroyer destroyed, 900 Allied casualties, and 482 Japanese casualties, including most of the men who loaded the weapons that achieved those hits. Innovation purchased with blood, proving itself through destruction, then fading into historical footnotes until researchers decades later rediscovered the modification through archival documents and material analysis. The torpedoes that struck USS Honolulu, USS St. Louis, and HMNZS Leander on July 13, 1943, carried no external markings indicating modification. They looked identical to standard Type 93 weapons. Only the chromium oxide layers hidden inside oxygen regulator assemblies revealed their true nature. Only the 11-mile range they achieved proved their effectiveness. Only the casualties they caused demonstrated their cost. Yamamoto's genius solved a technical problem through unauthorized experimentation. His tragedy was serving a military that couldn't systematically deploy innovation fast enough to change strategic outcomes. The modified torpedoes worked perfectly. They just couldn't alter a war already determined by industrial capacity rather than tactical brilliance. One mechanic's 18-hour gamble with electroplating equipment extended torpedo range beyond enemy detection capabilities, then vanished into footnotes when carrier aviation evolved past the battles where such range mattered. The 11-mile range capability existed. It succeeded. It killed. Then it became irrelevant.